Today we're going to discuss the structure and a reaction of conjugated pi systems. This chapter focuses on conjugated pi systems and paracyclic reactions, but we won't get to paracyclic reactions until the next video. First, we are going to focus on classes of dienes and appreciate whether they have electronic systems that interact with each other or not. In the first case, we have a conjugated diene, meaning that we've got pi bonds over the 4 carbons that contain sp2 hybridized carbons. So each of those carbons contains a p orbital, and therefore they are in conjugation with one another. Notice that for this point in time I have not shaded the orbitals. I'm just drawing that they are there. In the second system, we have an sp2 hybridized carbon an sp3 hybridized carbon that is separating the sp2 hybridized carbons, and therefore this carbon that's separating them is keeping them from being in electronic communication or conjugation with each other, and we can consider these as isolated pi bonds. The third type of diene that we will encounter is one in which there are 2 pi bonds spread over 3 carbon atoms, and these alkenes are not orthogonal, so they don't interact because the second double bond has to be at a 90-degree angle to the first one. So they don't interact because in order for pi bonds to interact, they must be simply side to side, parallel, and ready to overlap. Conjugated dienes can be made from the preparation of another alkene with a leaving group. A strong base gets you an E2 reaction across this carbon-carbon bond to produce a diene. That's one way you can make them. It's important to note that the lengths of the central carbon-carbon bond in a diene is different than that of another carbon-carbon bond with single bonds. With the diene, the carbon-carbon pi bond in the center is only 148 ppm in length, whereas in ethane, the carbon-carbon pi bond is 130 ppm in length. So what is the difference for this, given that these are both single carbon-carbon bonds? And the answer is in the hybridization, that the butadiene molecule has sp2 hybridized carbon atoms, and that means that the bonds between the carbon-carbon atoms will be shorter because sp2 orbitals are shorter than sp3 orbitals that occur in ethane. So recall that the more s orbital a bond has, the closer it is to the nucleus, which is what leads to this trend. Section 16.3 focuses on molecular orbital theory. Recall, let's go back to just the very basics. We're going to skip the s orbitals and skip the sp2 orbitals and the sp orbitals and only focus on pi bonds in this section. So when you have a pi bond, that means you must have an sp2 hybridized carbon or an sp hybridized carbon. When you have one of these carbons, you want to look to the adjacent carbon to see if it also has a pi or a p orbital. And if it does, then you can form a pi bond. And when you form a pi bond, you have to remember that you've got two incoming p orbitals, and they are going to form two pi orbitals. One of them can be written, one of them can be written with constructive interference, meaning that both of the p orbitals are in the same phase. And then the other, the pi star bond, is written with completely destructive interference. So electrons don't want to be in that bond. The electrons want to be here in the pi bond with constructive overlap. Some terms that you need to now know are the highest occupied molecular orbital, or the HOMO. So the HOMO, highest occupied molecular orbital, which is the highest energy orbital that contains electrons. And here it's not too hard to decide that this is the only orbital that contains electrons, so it must be the HOMO. But we'll see in other situations that there are multiple choices of occupied orbitals, so we have to realize which one to pick. The other term we need to know is the LUMO, or the highest unoccupied molecular orbital, and that's going to be, in this case, the only one that's not occupied. That is our lowest unoccupied molecular orbital. But again, as soon as we get to any situations that are more complicated than this, we will have to make decisions on which unoccupied molecular orbital is the lowest. Okay, let's take butadiene. This is a molecule with 4 p orbitals, which means that it is going to have 4 molecular orbitals. So what we want to do first when we're drawing a molecular orbital set for this molecule is to draw uncolored pi bonds at each sp3 hybridized carbon atom. And that I have already done for us at the bottom of this slide. Then the next thing we want to do is start with a first molecular orbital, the lowest energy one that has no nodes. And a node would be a line that went through 2 orbitals and switched their phase. So all of these orbitals are in the same phase. And this would be an occupied orbital, but it wouldn't be the HOMO. It would be actually the lowest energy occupied molecular orbital. Then we have to figure out what's going to go on with the rest of those orbitals, because we have used 2 electrons to populate the lowest occupied molecular orbital. But notice if you go back to the pi bond, you have 4 electrons to use in your bonding diagram. Let's go back to shading in our shading in our structures. So I mentioned the word node, and the word node means that you have a position between the atomic or molecular orbitals that changes their sign, and this is what it's going to look like. That once you go past this green path, the molecular orbitals have changed signs. So instead of being blue up, you have green down. And let's go ahead to the other orbitals and say how we are going to introduce nodes and fill in those signs. So this next orbital up that I'm drawing in has 2 nodes, and then the one at the top has 3 nodes, and these nodes tell us how to switch colors from one orbital to another. We know how to populate the orbitals because we know that we have 4 pi electrons to use. So that means we can populate this second orbital up. And now we've used our 4 pi electrons. And what that says is this is our HOMO, our highest occupied molecular orbital. And what this also says is that our LUMO, or lowest unoccupied molecular orbital, is the one above it. And these 2 orbitals are really critical to reactivity in organic compounds. We've definitely discussed a lot of reactions with nucleophiles and electrophiles, and we haven't been using molecular orbital theory to discuss them, but we could have been. And it's in chapter 16 that molecular orbitals really help explain what kinds of reactions are going on, which is why we introduced them again here, noting that we could have been using them all along, but it's just a general tendency of textbook publishers to ignore them until we get to this section on conjugated dienes. What about larger pi systems? Can we keep going? Yes. If we've got carbons with sp3 hybridization across all the carbons, we can keep building molecular orbitals. And hopefully this is going to start becoming intuitive to you, because we've got 6 pi bonds, and remember the rule of the lowest unoccupied molecular orbital has no nodes, so it gets a color on the same side as every pi bond. We know that the highest unoccupied molecular orbital, so here we're talking about this one, has every other carbon gets a change in sign. And now we've got to figure out what to do in between. And what I want to tell you before we start filling these out is that the HOMO, which is going to be this molecular orbital, that's going to look like the structure of your pi system. It's going to look like the double bonds that you draw. So when you're drawing double bond, space, double bond, space, double bond. That's what your HOMO gets. And that HOMO has 2 nodes. And that logic works. The molecular orbital below that has 1 node. The molecular orbital above it has 3 nodes. And there we add just 1 more node to the level above that. And then every time you have a highest molecular orbital, there's going to be a node between every orbital. Okay, so now we're starting to get into some reactivity, which is good because the rest of this chapter is about reactivity. So this portion of the chapter asks us to examine what happens if we have pi bonds that are conjugated, that are reacted with hydrobromic or hydrochloric acid. And before we are asked to look at what happens with conjugated pi systems, we are reminded of the mechanism of the addition of hydrobromic acid across a pi bond. And what we know is that when we have a conjugated pi bond, we're going to get Markovnikov addition of the hydrogen and the bromine across that pi bond. And that's because in the first step, when the pi bond picks up a proton, it has to leave behind a carbocation, and that carbocation is better resonance stabilized at the secondary carbon in this case versus that primary carbon. But what if you have 2 double bonds? What do you do then? Well, you can protonate the one of the alkenes. It does not matter which one. In this case, they're both the same. You protonate them, and you're left with the bromide leaving group. And now you've got 2 resonance structures to consider. Right. You can draw an arrow here that shows how you get to the second resonance structure, where the cation, it's not primary, we know we can't draw primary cations. It is a vinylic cation, meaning that it is stabilized by the alkene or vinyl group. So either the bromide ion attacks the secondary carbon or the primary carbon, leading to the formation of these two products. And what we see is that there is a difference in which product is formed based on the temperature at which we conduct this reaction. If we are at low temperatures, the first product appears where the bromine goes into the central 2 or 3 carbons. Whereas if we are at high temperatures, then we get a greater yield for the product going to the bromine at the less substituted positions. Why is that? That is because the bromine on the outer position is a more thermodynamically stabilized product. These reactions are reversible, and when given enough time and enough temperature, then we can get to the more thermodynamic product, which is the second one. Why is it more thermodynamically stable? It's because this alkene is disubstituted. Last, let's do an example together. Some of you have asked me to do some more examples in these videos. So what is the product of this alkene reacting with hydrochloric acid at 0 degrees? Now the first thing that stands out to me is that we've got 0 degrees as a low temperature, which means we're going to favor the kinetic product. So what's our mechanism going to look like? We can take either of these pi bonds, it doesn't matter because they're the same. Oh, let's back up a minute. I meant to use hydrochloric acid there. You're going to put that new proton on the less substituted carbon position. And now we need to consider that we are in resonance with this carbon carbocation. And the question is, of the two products that we can form, which one are we going to form? Now, given that we are at low temperatures, so we don't have the opportunity to get to the thermodynamic product. We are going to get to the kinetic product. Which is this. I want you all to be doing every in-chapter problem and get started on the end of chapter problems for chapter 16. And also, before the next time that we have a video together, I want you to draw resonance structures of the following compounds and figure out where a partial charge is. And I'll give you a hint with the first molecule. You can draw a resonance structure that pushes electron density to the terminal carbon atom. So we're going to get a partial negative charge there. And I want you to do that for all of these molecules in preparation for the Diels-Alder reaction. Have a great day, and I'll talk to you soon.